Now let's have a go at using mathematical induction to prove the sum of a series. And we're going to dive straight into an example where we need to prove that 1 cubed plus 2 cubed plus 3 cubed plus any number of integers cubed up to n cubed is equal to a quarter n squared n plus 1 all squared for all integers greater than or equal to 1. So let's think about what we're trying to do here. We want to start by proving that it works when n equals 1. Then we want to suppose that n equals k, and we want to show that it works when n is k plus 1, and then we want to bring all that together by showing that therefore it must work for all integers greater than or equal to 1. Now for the first part, let's call it A. We just want to let n equal 1 and show that this is true. So an easy way to set it out, state what the left-hand side is, state what the right-hand side is, and just show that they're the same. So the left-hand side is just going to be 1 cubed, which is 1, and the right-hand side is going to be a quarter times 1 squared outside of 1 plus 1 squared. Now notice there that I was just subbing in a 1 anywhere there's an n. I'm showing my working because it's a proof and I want to make it really easy and obvious for anyone to see what I'm doing. So I've got a quarter times 4, and that's 1, and that is equal to the left-hand side. So now I need to say, therefore, statement is true when n equals 1. And I'm finished the first part of my proof. Now I'm going to run out of board space here, so I'm going to rub out each part. You'll need to make sure you get it down. Just pause the video and go back if you didn't. All right, for the second part of my proof, I need to write this down. Suppose the statement is true for n equals k, where k is greater than or equal to 1. So that's just a statement that I need to write down every time when I begin the second part of the proof. Now, it's also important to really iterate what that means. That is, now here I've just literally copied this formula, but anywhere it had an n, I've put in a k. Now that's important because I'm going to use this statement in the next part where I prove that it works when n equals k plus 1. So next thing to do is to say let's let n equal k plus 1. All right, the left-hand side here is going to equal 1 cubed plus 2 cubed plus 3 cubed. Now I'm going to actually go all the way up to not just the last term, but the second last term. The second last term will be k cubed, and I'm deliberately including that because now it looks a lot like this statement above, but the last term will be k plus 1 cubed, won't it? Okay, so that's the left-hand side, assuming that n is k plus 1. Now I can actually use this statement above, and that's the whole reason that we put it in there, to say, all right, everything up to here, I've got above here, and I can see what that's equal to. It's equal to this stuff. So I can actually replace all of that with this, and that's what I'll do on my next line. I'll say that is a quarter k squared, k plus 1 squared. That's everything up to here, plus our last term. So now we can put that in. Okay, now we just need to tidy this up and prove that it equals the same as what we'd get if we subbed in k plus 1 where the n's are. Okay, so tidying this up, we could expand both of these and gather them back up, but obviously that looks like a lot more work. I think it's going to be easier here to factorize. So if you can spot that we've got k plus 1 squared as a common factor between these two terms, we can bring that out the front. And what we're left with is a quarter of k squared plus another k plus 1. All right, what can we do with this now? Have a look at our finish line. We want it to look something like this, but where we have a k plus 1 squared out the front. And if this is k plus 1, this will actually be k plus 1 plus 1, won't it? It'll be k plus 2 all squared. Now, the thing I can see here that looks really different between what I have and what I'm going for is that this one's got that big quarter sitting out the front. And my quarter is kind of caught up here inside brackets. So I'm thinking my next step is to actually bring the quarter out the front of the brackets. Now what I'm doing here is I'm leaving this part out the front, and I'm basically bringing a quarter out of this part here. So what will I be left with? Well, I'll have k squared. What needs to go here and here so that when I do a quarter of something, I get k? Yep, that's right. It needs to be 4k plus 4. So that if I expanded those brackets out, I'd get what's inside these brackets. Does that make sense? All right, we're getting there. It looks to me like we need to bring that quarter right out the front, so it looks like our finish line. And then we've got our k plus 1 squared, that can stay there, because if we sub in k plus 1 for n, that's exactly what we'll have out the front. And now this part here just needs factorising. Can you spot what we need? Yep, it's a perfect square. It's k plus 2 all squared. Okay, this actually now looks exactly like the right-hand side as it would look if we subbed in a k plus 1 there. We would have k plus 1 all squared, and we subbed in a k plus 1 there, which would give us k plus 2 all squared. So we're close enough now to say that that equals the right-hand side. Okay, so that's the second part of our proof. We've proven that n equals k plus 1, but we haven't written a statement about it. After that, I didn't need to go on the next line, but obviously I've run out of board space here. I'd write, therefore, the statement is true when n equals k plus 1. So the statement is true for, or when, doesn't matter which, n equals k plus 1. All right, and it's very important that you write that. There's no point proving it and then not stating it. You've got to be really deliberate about stating what it is that you found. And then we finish off with part C, where we write down, it follows from parts B and C by mathematical induction that the statement is true for all positive integers n. Okay, so we've really told a story here. We've said it works when n equals 1. If it works when n equals k, which it must, because you can easily just change the pronumeral there, where k is greater than or equal to 1, then we've proven that it works for k plus 1. So if it works for 1, it would therefore have to work for 2. And if k was 2, it would have to work for 3. If k was 3, it would have to work for 4. And therefore we can say, by mathematical induction, it's true for all positive integers n. Now notice that we're only looking at positive numbers here, and we're only looking at whole numbers. For our next example, we need to prove by mathematical induction that for all integers greater than or equal to 1, the sum of a geometric series is this formula that you've already learnt how to use and should be quite familiar with by now. So the first part of our proof, we need to just let n equal 1 and show that it's true. So the left-hand side, when n equals 1, would just be a. And the right-hand side, when n equals 1, we would have a r to the power of 1 minus 1 over r minus 1. Now here you can clearly see that we've got r minus 1 on the top and the bottom, and they cancel, giving us a, which is equal to the left-hand side. Therefore, the statement is true when n equals 1. And it's important that we write that. Okay, that's the first part done. For the second part, we need to write out this statement every time. Suppose the statement is true for n equals k, where k is greater than or equal to 1. Now you'll get used to writing this because you need to write down these words every time. Then you need to iterate exactly what that means. What you're saying is, in other words, this same statement here with an n in it is going to be now written with a k, and this part with an n in it is written with a k. Now, that seems tedious to write down, but it's important because remember we're going to use that on the next line when we look at the situation of n equaling k plus 1. So next we need to let n equal k plus 1. All right, the left-hand side, when we have it equal to k plus 1, now we're going to write out all the terms, including the second last one and the last one. So we'll go dot, 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 and, whoops, only 3 dots, ar to the k minus 1. Now we're going to go for one last term, which is we're subbing in k plus 1 here. So this is going to be k plus 1 minus 1. So obviously it's going to be ar to the power of k. All right, now tidying that up, we know that all of these terms here equal this. So we can actually just jot that in, r to the k minus 1 over r minus 1 plus ar to the k. Now we need to tidy this up and make it into one expression, because what we're going for is something that looks like this, but that's got a k plus 1 where the k is. So looking for clues on what to do here, I mean, we're adding some things and one of them is a fraction. Makes sense to me to make common denominators. So what we could do here straight away is say, and you can include as many lines of working as you need. Some people will happily leap 2 steps ahead and you'll want to show a line in between. You need to show enough lines of working that an examiner can see exactly how you went from one step to the next. But if you're nervous of making a mistake, show that extra line of working, because by the time you can think something, you might as well have written it. Okay, so here I'm going to say I've got ar to the k, and I'm going to put it over r minus 1, and I'll put this multiplying the bottom and the top by r minus 1. Now on the next line, I can see that that gives me both terms over the same denominator, and I can actually expand out what I have in both sets of brackets at the same time. So I've got a r to the k minus a, and over here I've got, now what happens if I have a r to the k and I multiply it by another r? Well, isn't this r to the power of 1? So when I multiply and the bases are the same, don't I need to add the indices? So that means that this term gives me a times r to the power of k plus 1. A r to the k plus 1, to extend this line a little bit, and then multiplying this by negative 1, I get minus a r to the k. All right, we can see here that we've got a r to the k minus a r to the k. So those two are going to go, and we're left just with these terms here. Now, having a look at your finish line helps. We're trying to get it into this sort of form. So that makes it obvious to me that we need to bring an a out the front and factorize this thing. So running out of space a little bit, let's continue on over here. Bringing an a out the front, I'm left with a negative 1, and I'm left with an r to the k plus 1. Well, I'm going to write that first because it's positive, so it looks neater, but also it's going to get it in the same form as my other part here. And on the bottom, I've got my r minus 1. So I'm there. Now, all of this is now equal to the right-hand side. And how can I tell? Well, it looks exactly like the right-hand side looked here if I'd replaced the k with k plus 1. So I've proven that it works for n equals k plus 1. So I need to write down, therefore, the statement is true for, or when, doesn't matter which word you use there, for n equals k plus 1. And then we finish off the same way every time. Part C of our proof is to say it follows from parts A and B by mathematical induction that the statement is true for all integers n greater than or equal to 1.